In this lab, we explored the idea that there was a charge in everyday household objects, and really in any object. We used two pieces of tape for the experiment, and after proving that there was in fact a charge, we were able to use what we know about how to calculate the force of electric charge on an object, along with what we understand about Newton's laws, specifically his second law of motion, the momentum principle. So I started out with two 20 centimeter pieces of tape, or 0.2 meters, which we know have a weight of about 1 gram per meter or 0.01 kilogram per meter. So from this, we know that both pieces of tape will weigh around 0.0002 kilograms. For my experiment, the tape began to float above the other at around 3 millimeters or 0.003 meters. And with this information, we can start utilizing the momentum principle by first calculating the force on the tape due to gravity, which you can see here. And I calculated it here using 9.8 times the mass. And since the floating tape is at rest, we know from the momentum principle that the net force on it must equal out to 0. Therefore, since the only other force acting on the tape in this situation is the force of the electric charge, we know that it must be equal and opposite to the force of gravity, which you can see here, and you can see the afterwards the calculation. And now that we know what the force of the electric charge is, we can solve for the tape's electric charge. And you can see the calculation for that right here. And this comes out to be roughly 1.4 times 10 to the negative 9 coulombs. Now, throughout our calculations for the experiment, we had to make a few assumptions. First is that we completely ignored the air resistance. So when we have this gravitational force going down here, we have the electric force going up, as you can see in the model. In the real world, there would also be another arrow going upwards, which would be the air resistance, and that would lower our calculated value for the force of electric charge, and therefore our calculated charge. And also for simplicity, we decided to treat the 20 centimeter tapes as just the charge on a single point. And that pretty much means that we concentrated the entire charge of the tape onto one point when we did our calculations for simplicity. And finally, we made the assumptions that both tapes had the same evenly distributed charge, when in reality, the same force we calculated upwards here could be created with one tape being a higher charge than the other. Looking back, there are a couple of questions to consider about this experiment too. First of all, what if the electrons had positive charge and the protons had negative charge? Well, essentially, what this asks is, what if the signs on all the charges were flipped? And that's exactly what would happen. Just the signs, all the charges would have opposite signs in our calculations, but in the real world, the interactions between protons and electrons would be the same. They would be completely unaffected. Us changing what we conventionally determined to be the sign of a proton or the sign of an electron doesn't affect the real world physics of the experiment. So ultimately, our results wouldn't change. They would have the same absolute value. Additionally, we have to consider why it was important to handle and touch the charged tapes as little as possible throughout the experiment. And the answer is quite simple, actually. When charged tapes come into contact with our hands or other objects, they could easily transfer electrons, lose or change their charge, and then in the example that like they lose their charge, two nearly chargeless tapes don't exert a noticeable enough force on each other for us to be able to uh, find any like observations and conduct this experiment. And so with that, I thank you for watching and I hope you have a great day.